It's great to be back at UT. I was here, I think, in 2019, around the same time. And it's great to see the students filling a room. How many people here are undergraduate students? Okay, don't be shy. How many people are master's students? And how many PhD? Okay, how many people are like postdocs or other researchers? I guess, yeah. How many people are faculty? Okay, it's good to know. I think I did the right thing by being broad. I expected a broad audience like this. So a lot of this talk will be about motivation on what we're doing wrong in our systems from my perspective today and how we can potentially fix it. I have a lot of slides. It's better if you focus on what I say as opposed to what's written on the slides, because I tend to have very high bandwidth speed in terms of progressing towards slides. But feel free to stop me if you have questions also. Does that sound good to everyone? Okay, let's get started. So I'm going to talk about memory-centric computing. I think it's clear to everyone today that computing is really bottlenecked by data. Important workloads are all data intensive, machine learning, genomics. I'll give some examples. They require rapid and efficient processing of large amounts of data. And data is increasing. Basically, today we can generate much more data than we can process in many domains because our data generators are quite strong. We actually have great technology in data generation, but we don't have great technology in data analysis, I would say. And we also need to perform more sophisticated analysis on data, and people want to do more in applications, for good or bad. This is an example. Clearly, everybody is fascinated about machine learning today, and machine learning actually puts a lot of pressure on both memory and computation. And both of these requirements are growing exponentially, essentially, as we increase the size of the machine learning models. By the way, this is a nice talk by Cerebrus's Chief Technical Officer, Sean Lee. I would recommend people to watch it if you're interested. These guys are building wafer scale chips, basically chips that are this big, essentially. And they want to put, and one of the main reasons why they want to build wafer scale chips is they want to put large amounts of fast memory together with large amounts of compute, mainly to tackle this bottleneck. In a sense, their chip is an example of a memory-centric computing paradigm. Still, it's not perfect in the sense that memory and compute are decoupled from each other. So this will become more clear as we go through the talk. Okay, so there are a lot of interesting workloads that we're dealing with today. I'm not going to go into detail in a lot of these. These are growing in terms of sizes. And data is a performance and energy bottleneck. I'm going to give you some numbers also to substantiate this claim soon and a little bit later in the talk as well. And these are the large-scale workloads that are run in data centers, for example. There are also workloads that are run in mobile systems and edge systems, et cetera, some of which we're using right now, actually. Well, kind of. Zoom is part of this ecosystem, if you will. And data is a performance and energy bottleneck on them as well. I'll talk about something that we're working on that I'm quite excited about, which is genomics. This is an area I like a lot because there are a lot of interesting problems to solve in genome analysis. And essentially, we are able to generate genomic data much faster than we can process it. So this picture, this is a relatively old one over here, but it shows the cost of sequencing a genome. It's been reducing greatly, exponentially, and inflection points correspond to the introduction of new technologies, new sequencing technologies. I won't go into a lot of detail, but I'd be happy to talk about it. I'll also be happy to talk about anything in this talk or beyond in Yale's class that he mentioned at 5. So you can see that the cost of sequencing a genome is reducing greatly, but the cost of a transistor is not reducing as fast, assuming this Moore's law still holds. This means that we can generate data at much lower cost than we can put transistors on a chip. And again, this is old data, but the trend continues. And clearly, genome sequencing is bottlenecked, leads to scientific discovery and medical advancements. And we're really bottlenecked by how fast we can process the data and how efficiently we can process the data. Again, I don't want to go into this detail. Clearly, there are many applications of genomics. Many more will come. I don't want to turn this into a genomics lecture, let's say. But I'll give you an example of the sequencing device. So this is a fascinating technology. It's a nanopore sequencing device. Basically, it passes DNA or RNA through a nanoscale hole. And that nanoscale hole, while the DNA passes through that hole, you make current measurements. Essentially, you can correspond the current measurements to the basis of a DNA, for example. And then you actually do later mapping to a reference genome and then many analyses downstream. So this is a great data generator. It's actually very fast, very high throughput. You can actually have arrays of these. This was used for example, understanding the COVID genome significantly. Unfortunately, this is a terrible data analyzer. You generate a lot of data. You have to move the data from this device to somewhere else, at least to your laptop, which is usually not powerful enough to do any interesting analyses, or to a data center somewhere else. Wouldn't it be nice, actually, if you had this device capable of interesting computation, interesting analyses, powerful enough to do that, so that you can actually do the analyses that you want in your hand privately, potentially, right? Or a doctor could use this also. I'm showing you this because this is one example device. And I think we're having this problem in many systems today. If you remember only one slide from this talk, maybe this is a good one, at a high level at least. Basically, we have very special purpose machines for data generation today. This is another sequencing device. They're very fast in what they do. They're very specialized, and they generate a lot of data. But they're completely incapable of processing the data. You need to move the data to a machine to analyze the data. Usually, they're general purpose, and they're slow. So we have two problems, essentially, I would say. One is we move the data a lot. We have large amounts of data moved in our systems. And we also have slow and inefficient and non-specialized compute capability that doesn't match the specialization levels that the devices that are generating data at. And if you don't like genomics, replace this with video cameras all over the world. Replace this with clicks that are happening on the web. Replace this with any action that is actually generating data at a large scale. OK, so if you're interested in genome analysis, I'd be happy to talk about it. We've written a lot of papers. These are some primers. We're working on accelerating it using better algorithms and architectures. OK, so hopefully I've given you one example of data increasing. I will also show that data is really overwhelming our machines today. So today we build machines with high storage capability, high communication capability, and high computation capability. In the end, data is really overwhelming all of those. And data is also greatly impacting robustness, energy, performance, and cost. We're going to look at the interactions of these elements. So if you go back to the fundamentals, a computing system needs computation, communication, and storage, or memory elements. And the way we've designed them so far has been decoupled, in the sense that computing unit has been kind of the king, if you will. That's the only place where you can process the data. The communication units and the memory and storage units are essentially dumb. They cannot do anything to the data. They can store the data, but they cannot act on the data. So this is at the micro scale as well as the macro scale. This is what we do. The device that I showed you kind of also showed that a little bit. There are also sensors. I will show that later on. But basically, this sort of design, in my opinion, has cost us a lot. It enabled a lot of things, but right now it's costing us a lot. Let me give you my cartoonish picture. This picture I drew actually in 2008. I still use it because nothing much has changed in general purpose systems. So if you look at a general purpose processor or a special purpose processor, it usually consists of cores that can do computation. And then the rest is some caches or buffers, some interconnect, other caches or buffers, other interconnect, and then memory controllers, other interconnect, memory, and other interconnect, and then storage. So if you look at this picture, and if you actually do the calculations and trends, you basically see that more than 95% of the real estate of a single node is dedicated to data storage and movement. Compute units are actually very small. So you would think if you actually showed this picture to a child and said, oh, do you have a data movement problem? They would probably tell you, no, you're actually using all of your resources almost for data storage and movement. But that's not the case. Basically, the system is still bottlenecked by memory and storage today. So I think by looking at this picture, maybe we can think about how we can design better systems. So if you don't like my picture, this is a real chip from AMD. That box over there is essentially the L3 and L2 caches. I'm not even including the memory interconnect over here and memory controllers and the caches inside the cores, buffers inside the cores. So this is real. And we're adding more. So AMD is adding, with beautiful technology, 3D stacking technology, another cache chip on top of this. So this really makes sense to actually keep growing this paradigm where we actually do computation only inside the cores. OK, if you don't like AMD, this is IBM. Again, that green box corresponds to some part of the data storage. But you can also see that a lot of the chip is actually about accessing memory, accessing outside, memory signaling, PCIe, et cetera. So computation is, I'm not going to call it a solved problem, but computation is not our problem today, I will argue. So our problem is really about how to move the data, how to supply the compute units with data, and how to actually process that data efficiently. OK, there's another chip over here, or SoC. This is actually interesting because if you look at the chip itself, it's a lot of SRAM. And then you have a lot of DRAM, and you have even more darkness which is a storage, which you usually forget about. But that's actually, if you look at the transistors dedicated to the entire the infrastructure, computing infrastructure, most of it is actually in the storage today. And they're sitting idle, doing nothing on the data. And you have to move it all the way from storage to the processor. OK, let me give you some numbers. We did a lot of analyses on interesting workloads. I'm going to give you more numbers later on. But we did this analysis with Google on these workloads on average use cases. And we found out that more than 60% of the total system energy is spent on data movement within the memory hierarchy, from the memory to the CPU. These are not extremely intensive workloads. If you go to very intensive workloads, like very large machine learning models, the numbers actually become even more substantial. So more than 90% of the total system energy is spent on memory, accessing memory, moving data out of memory, inside memory, in large machine learning models. So I think at this point, we're not designing architectures that are intelligent. If you actually want to design architecture that's processing data, it needs to actually handle data well. So what does it mean to handle data well? There's a bigger research agenda over here that I'm not going to talk about in detail, but I'm going to focus on the first one. We need to ensure data doesn't overwhelm the components. If you're interested in the other ones, like taking advantage of large amounts of data and metadata to actually improve the system over time, like using machine learning on the data so that you can design better architectures that can learn from their actions in the past, feel free to ask that question in Yale's course. We don't have time for that. And then also, we're not communicating about the properties of the data from the higher levels to the lower levels today. Data has a lot of properties, but a lot of those properties don't get communicated. As a result, you cannot really process the data in an intelligent manner. But I'm going to focus on the first one since we don't have a lot of time. And that's actually the dichotomy between processor-centric systems versus data-centric systems. So before I move on, I will say that a lot of what I'm going to talk about requires thinking across the stack. We're not going to be able to, I believe, at least initially, to just change one layer and make sure that everything works very well. We'll need to think about new ways of doing computation inside memory, as we will see, and then new algorithms to take advantage of it, potentially. And then everything else in the middle needs to be designed as well. OK, so let's jump into data-centric and memory-centric architectures. Feel free to ask questions, by the way. I know we're motivation, but there'll be a little bit more motivation also before we get to part of it. And then I'm going to ask you a question if you don't ask me a question. OK, so a data-centric architecture, actually, if you think about if data is the most important thing that you design, for, what should you do? I think that's the question we're asking. Today, we're implicitly assume that the processor, computing unit, is the most important thing. As a result, everybody serves the processor. But if data is the most important thing, what do we do is the question that we're trying to answer. There are many aspects to this. I'm not going to cover all of them. I'm going to cover the first one, which is processing data where it resides or where it's generated or where it makes sense in general. But I think we need to also think about how we access data, much better lower latency, lower energy data access structures. Emerging technologies are very interesting. How to make it lower cost to store data and process data, and how to much more intelligently manage data. I think these are very interesting directions, but again, we don't have time to focus on that. So let's jump into processing data where it makes sense. So here I say where it makes sense. That means that if you're trying to optimize a metric like performance, energy, reliability, usually it's a combination of all of those metrics, figure out the best place to process the data. Don't assume that it's the processor. Today we have no option. You have to go through the processor, accelerator, some computing unit. But we have many options actually, in potentially, if you think about the data-centric system. We can process the data in all of these structures, wherever it's generated, while it's communicated as well. Clearly, this idea is not a new idea. This is the first incarnation of the processing in memory idea that I've seen. If you find older papers, please let me know. It was called Logic in Memory, as you can see in the 1960s. And these people essentially have proposed putting logic close to memory structures. I'm going to later term this as processing near memory. And there's another paper by Harold Stone, whose book you may actually have studied in the past. I found that book while I was a PhD student with Yale, in Yale's, I guess, library, and I read it. It was fun. OK, but basically, this is an old idea. You may, of course, ask the question, it's been like 60 years almost. What's changed? Like, why are we interested in this idea again, if you will? We can also talk about the other issues related to this, but I believe we actually have nowhere to escape today. And I'm going to motivate it from two directions. If you look at the computing stack, there's technology at the bottom, devices, circuits, et cetera. And then there's applications and systems at the top. And we're having problems with data on both sides. So technology, essentially, technology scaling is not going very well. we're not able to scale the technology size, the size of memory cells and get high reliability, high performance, high robustness. And these issues actually demand intelligence in memory. Intelligence meaning that you need to actually do something better than what we're doing today. Sorry. You need to do some computation near memory to actually make sure that the memory actually works for storing data. And I think this is very much data-centric because you're doing computation next to memory to make sure memory works. The other side, there's a huge demand from application and systems. We have a huge data access bottleneck. I've kind of motivated that. Energy and power are big bottlenecks in our systems today, and data moment energy is dominating computing energy. I'm going to show a little bit more about this. And today, we're also very greedy. We need performance, energy, and sustainability all at the same time. We don't want to trade off between any of these. We want to improve all of those metrics. And I think for good reason, because we're having a lot of problems, and we don't want computing power to keep exponentially increasing to cause even more problems than what we have. Okay, and I believe we can improve all metrics by minimizing data moment. So our designs are squeezed in the middle. We don't have anywhere to escape. That's why I think we need to be data-centric. Now, if I was giving this talk 4 years ago, which I did, I wouldn't be able to show this slide, or at least part of the slide, and I didn't. So people are actually doing this today. This is old. People are basically using 3D stacking technologies where you have a logic layer underneath memory layers, and then you can actually do computation in the logic layer. And people have been experimenting in the past. But since 2019, there have been actually interesting, significant developments. How many people were here in 2019 when I gave this lecture? Hopefully only the person. Okay, you were here. Maybe a PhD student. I did not have this in the picture. Basically, this is a company in France. They modified the DRAM chips to put essentially a general purpose multi-threaded processor next to each DRAM bank. So you can actually buy this, program it, and see the effect on applications. It has a lot of idiosyncrasies because it's the first generation technology. But even though it's the first generation technology, if you carefully optimize your applications, you can outperform existing CPUs and GPUs because you don't move the data out from the DRAM chip. You can process the data inside the DRAM chip. I think this is fascinating, of course. Not only UpMem, but major players like Samsung have introduced DRAM chips where they can do computation near memory. These are more specialized. You can do essentially a lot of matrix operations, multiply and accumulate operations. SK Hynix has something similar. People have also been developing boards where they can do processing, like here, a chip. They're adding a chip connected to many DRAM chips over here so that they can do near memory processing. And Alibaba has also introduced their chip to accelerate machine learning models that they use internally. So I think it's happening. We'll see if it survives. But I think these are all steps in the right direction. And there are many other experimental chips and startups that I'm not talking about here. People are experimenting with processing in SRAM, RRAM, et cetera. And there's also other interesting action happening. There are interconnect technologies that people have introduced, like Compute Express Link, for better scalability of essentially memory. But people are using these technologies to accelerate applications by pushing computation closer to memory. So this is another example of near memory processing from my perspective. And again, major players are introducing these. In fact, one of the major conferences in computer architecture has multiple papers on this topic soon in March. Okay, now let me take a step back here. Why is this happening? I think this is clearly happening because of workloads and scaling. But I like to also take a lower level perspective because I think these are synergistic. So we've been arguing for a long time that memory scaling is not going well. We need intelligence inside the memory to solve many issues, including application acceleration. I have to talk about RowHammer. Yale told me, don't talk about RowHammer, but I'm going to talk about that because I think it's related. How many people know about RowHammer here? Okay. How many people do not know? Don't be shy. Okay, that's good. Still, it's useful, perhaps. So basically, this is the phenomenon that you can predictably induce errors in most DRAM memory chips. DRAM, dynamic random access memory chips, are the chips that are used for building main memory today. Essentially, everyone has DRAM chips. And I'll give you the basic idea. The basic idea is if you keep accessing a row, when you access a row in a DRAM or in any memory, you apply high voltage to that word line to access the cells that are connected to the word line. And if you keep activating that row or applying high voltage, and then closing that row, applying low voltage, which is the normal operation that you would do if you want to access one location in memory and then access something else later on. If you keep doing this, activate, precharge, activate, precharge, activate, precharge, activate, precharge in DRAM, you would get bit flips or modified data in physically adjacent rows. Clearly, this should not happen, right? You're just reading one row. You should not be changing anything in memory, including in that row. But this is happening today. And this is because cells are too close to each other. There's not enough electrical isolation. And we want to actually push and have a lot more memory capacity inside a single millimeter square. I will not go into the details of this. Again, if there are questions, please either ask or leave it to Yale's lecture at 5 p.m. So all DRAM chips are vulnerable to this. Don't worry about those 80%. Today, things have become much worse compared to when we first analyzed the problem, that all DRAM chips actually have this problem because cells are too small and too vulnerable to noise. And people have shown that this is a security vulnerability. Basically, if you can predictably induce these bit flips, as a result, someone can, who has user-level access to your computer, can actually use these bit flips to take over the system or steal some data that they're not supposed to access. Again, I'll leave it at that. But this is a scaling problem, and we have written papers about it. So how do you solve the scaling problem? We've always argued that you need to, unless there is a low-cost technology solution to the problem, or you go to some emerging memory technology, you need intelligent controllers to solve this problem. Intelligent controller essentially detects, for example, some of these rows that are being hammered or accessed a lot, and prevents access to them in some way, or refreshes the adjacent row to make sure that the data stays intact. Now, the good news is industry is finally on board. This is from ISSCC. SK Hynix published a paper where they essentially did that in real DRAM chips. This is intelligence in memory. Basically, they have counters associated with cells, each DRAM row, and they monitor the counts of accesses, number of accesses that have happened to each DRAM row, and take preventive actions. This is hopefully going to happen in future generations. I'm not suggesting this is perfectly secure or anything. I believe we'll have a lot more problems like this going into the future, but this is also a step in the right direction. We're adding intelligence inside memory. This is computation inside memory, essentially, to ensure that memory works correctly. And Samsung, after seeing SK Hynix's paper, they had to put a not so well-written paper on archive. Okay, so basically, are we now bit flip free? And the answer is no. We keep finding these bit flips. This is something that we found in ISCA this year, last year, 2023, where we show that there are other redisturbance phenomenon that actually make the bit flips much more prominent in DRAM. Again, I'll leave the suspense over here. You can ask me questions about it later. Okay, so you may say that, okay, DRAM is old technology. It's been around since 1965. Why are we still dealing with it? And I agree partially. I think we should be investigating emerging technologies. The unfortunate fact that there's no perfect technology. Essentially, emerging technologies all have the same problems, or existing technologies like SRAM, Flash, they all have the same problem. As you scale them to very small sizes, you will have some sort of noise reliability issues. So you'll need to actually build intelligent controllers to actually overcome this. If you look at a flash memory system today, for example, an SSD, if you look at flash memory, actually, when you manufacture it, especially at the scale that we're manufacturing today, most of the bits don't work. What makes those bits work is controllers that are actually doing actions like what we described. Okay, so hopefully I've convinced you that intelligent memory controllers can avoid many failures and enable better scaling. Any questions? Okay, everything's clear then. Okay, so I'll move on. So on the systems and application side, I'm going to go through this relatively quickly so that we can get to some new ideas also. We basically have a lot of problems with data access, energy consumption, and data movement energy dominating computing energy. So I think from a bigger perspective, I believe we need to think about what we're doing with computing. Do we really want to design systems the way as business as usual, and then maybe not have a good world that looks like this? Or do you want to live in 1940s Pittsburgh or something like that? I believe in the end, humans are greedy. We want high performance, but we also want energy efficiency and sustainability all at the same time. And if you want this, I think we're doing absolutely the wrong thing. Because our current design principles, which is having processor-centric systems, is really causing great energy waste by moving the data around, but it's also causing great performance loss, despite the fact that we've developed a lot of techniques to overcome the performance loss, like what Yale teaches in his microarchitecture class, like out-of-order execution, prefetching, many levels of caching hierarchies, many levels of multi-threading. All of them are there, mostly, to tolerate long latencies, which is memory latency today. Unfortunately, when they work, that's good. When they don't work, or when they help work, they waste a lot of energy, and they waste a lot of resources. So I think we need to rethink our system in terms of how we design it. And when you actually have this, and this is also a vicious cycle, I think. You actually add more complexity to your system so that you can overcome something, but that causes even more energy loss, right? Energy waste. So we're in this vicious cycle today. How do we get out of this vicious cycle? I think identifying that we're in a vicious cycle is the first step, and the second step is fixing it. So I think the vicious cycle is processing of data is performed far away from the data, and we need to fix it somehow. So I've already shown you this picture. I'm going to go through this relatively quickly. Basically, we design processor-centric systems. All data gets processed in the processor at great system cost. And we know that this is bad for performance. How many people know about Dick Seitz here, Richard Seitz, the author of this article? Well, the professors. So this person was a chief architect of the Alpha systems, which was one of the leading processor designs at the time. And after they designed a flagship Alpha chip, he basically wrote this paper. It's a one-page paper. I'd recommend you to read it, from 1996. And he basically titled this "The Memory Stupid." He basically said, we designed this processor that's capable of finishing 4 instructions per clock cycle. But unfortunately, on this important workload, a database workload, that we actually think we designed it for, it's finishing 1 instruction every 4.7 cycles, meaning it's operating at about 5% of its peak capacity, or peak computational capacity. And he basically concludes the article saying that, and why? Because it's waiting for data to come back from memory, essentially, even though it has a pretty good memory hierarchy compared to that time, right? And he basically finishes the article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. It is an important design issue, but we need to actually, I think, make it an even bigger design issue going forward. This is data from my own PhD thesis. You will recognize this slide. We did this study with Intel. Basically, we show that most of the time, the processor is waiting for data. This is 10 years later, about 10 years later. And you can read the paper that Yale mentioned. 10 years later, if you don't believe Dick Seitz, if you don't believe us, this is Google. Since everybody believes Google, this is Google's data from 2015. According to them, this is all of their data center workloads. And essentially, they show the same thing. Most of the time, the processor is waiting for data. OK, that's the performance perspective. Basically, we're wasting a lot of performance capacity. We have actually very powerful processors, but we cannot feed data to them. Let's look at the energy perspective. This is a slide that I borrowed from Beldali. And actually, this is interesting. You can argue with all of these numbers here, because it's old technology, but the trend remains. A 64-bit double precision floating point operation, complex computation basically, is 20 picojoules, and memory access is 16 nanojoules. So it's 800x difference. Now think about this. If you actually want to add 2 numbers, you need to do 2 memory accesses, assuming they're not in the same cache block. You bring the data into the chip, and then you write the data back. So you do 3 memory accesses, and if you don't have a lot of locality, you basically are wasting a lot of energy just to do a very simple operation. This is actually our success, I would say. The reason we're here is because of the technology scaling improvements that we've seen over the last 50 years or so. Computation has become very cheap in terms of both latency and energy. Unfortunately, memory access did not scale as well, interconnects especially. As a result, we're in this situation. And today, people are actually pushing many workloads to be simpler in the sense that you don't want to operate on large amounts, data widths, or you don't want to do very complicated operations, let's say. And if you actually look at a 32-bit addition operation, that's 6,400x less energy than a DRAM access. Now, you can do the calculations if you're taking computer architecture, especially. You can do the calculations to figure out how much locality, how much reuse do you need in your caches to overcome this energy differential. And that's a lot of reuse. And that doesn't exist in most workloads today. And especially the workloads that are really interesting, that access a lot of data. OK, so that's the reason why we actually see these numbers. More than 60% of the system energy is spent on data movement. In not so intensive workloads, I would argue. And intensive workloads, more than 90%. In many cases, 99.x% is spent on memory. OK, so basically, hopefully this is all arguing that we do not want to move data. Essentially, we want to change our mindset or paradigm to enable computation with minimal data movement and compute where it makes sense to, or where data resides to enable this. I think this is really part of what's about making computing architectures more data-centric. Now, I'm going to talk about some mechanisms to achieve this. And then since you haven't asked me a question, I'm going to ask you a question soon. So basically, we're going to talk about especially processing inside memory and storage devices. You could extend it to sensors, network, etc., or even processing in the cache. Even that is not done today, for example. That's easier to do. I'm not going to talk about that. Essentially, we can store a lot of data, a lot of interesting applications in memory and storage. And we want to be able to say, memory, please execute this function or this application for me on this data. And memory says, OK, I can do it. Here are the results. So this is an accelerator type of model. We're going to be less aggressive. You can also imagine a future model where every component that you design is an independent agent, and they can actually do computation. Here, processor core is still orchestrating the computation. So there's still many questions over here. How do you design the compute-capable memory and controllers, processors and communication units, software and hardware interface to enable this? Now, the good thing about the CXL interface that I mentioned, Compute Express Link, that enabled an interface over here that is capable of offloading computation to the memory side, which is not easily doable in other interfaces that are not flexible. If you didn't understand that, don't worry. So system software compiles on languages. How do you enable the stack to enable programmers to actually take advantage of this? And how do you actually enable new algorithms to take advantage of the devices? Because devices may have capabilities that are not similar to the capabilities that we have in today's processors. And I'm going to mention that especially. I should also say that theoretical foundations. So if you think about how many people have taken a computing theory course or theory of algorithms course here? Well, if you have taken it or if you're going to take it, you're going to count operations. Essentially, you're going to analyze the complexity of algorithms by counting operations. And I would argue that that's a very processor-centric paradigm or theoretical paradigm. If you actually want to be more data-centric, we need to reinvent the theory aspects as well. I'm not an expert in this, but I believe people need to reinvent that. OK, so now let me go into some new ideas. If you're interested in this area, we keep expanding this paper that's on archive that talks about what's happening in this field. And we also have a processing in memory course and a bunch of courses that are related. And we have tutorials in major conferences. These are all openly available online on YouTube, etc. I would argue that we need to think differently from the past approaches also. In the past, people have put different processing in memory engines. I will not go through them, but I think we need to think a little bit differently. Here, I'm going to define some terminology. I think there are two major types of processing in memory. I'm going to call one using memory and the other near memory. I believe these are two fundamental types and no other type exists. I'd be happy to be proven wrong. So you have a processor, computation unit, and you have memory. Processing near memory is taking the logic or computation unit and putting it closer, such that at some point it's integrated in memory. It can be in the DRAM chip. It can be next to each cell. But memory is memory. It cannot fundamentally do computation. Logic is logic. So you need to still move the data a little bit. That's processing near memory. You put the logic closer to memory. This is what people have envisioned in the 1960s. But today, I believe there's something also very exciting that people are trying to do, which is processing using memory, which has its roots in analog computation. The idea is you have processor today and memory today, or logic or computation. Forget about the logic and computations. Take the memory device. Think of what this memory device can do in terms of computation. Today, we treat it as memory device. We read or write and refresh. But we cannot tell memory, do AND, or do or copy data. Basically, processing using memory says, exploit the analog operational properties of the memory circuit and device to do computation, not just data storage. And this is fascinating because fundamentally it's analog in nature, and making it work is not easy. So in that sense, processing using memory is longer term. Processing near memory is shorter term. And I believe in the end, they need to be combined so that we can actually do interesting and powerful processing. So now my question to you is, which one do you want to cover? Longer term, exciting processing using memory? Shorter term, boring processing near memory? No, it's not a leading question. Who says using memory? Who says near memory? OK, yeah, I think using wins. Sorry, I had to. I'm happy to talk about near memory. But basically, everything I showed in the picture, and we do a lot of work on processing near memory, don't get me wrong. I think work needs to be done in that area. There's a lot of exciting research. But all of the pictures that I showed in real chips are processing near memory devices. Processing using memory is a bit harder to implement in real life. But our goal is to actually enable the implementation of it. OK, so let's jump in. I'm not going to go through the taxonomy, but I talked about the nature of processing in memory, using or near. But then you can also think about different technologies, and we have many technologies. And you can also think about different locations. And in the end, a tuple determines the processing in memory type. I'm going to treat memory as an accelerator. Basically, we're going to have an accelerator on the memory side that takes advantage of the analog operational properties of memory, specifically DRAM to begin with. And essentially, we're going to talk about processing using DRAM in main memory. It's interesting. That's essentially terminology. So basically, the gist of it is that we've shown that you can support bulk bitwise AND, or NOT, and majority operations in DRAM. You can do bulk bitwise copy and initialization and zeroing operations. You can do true random number generation in DRAM. All of these are shown in real DRAM chips as well as in simulation. You can do lookup table-based, more complex computation, which is not shown in real DRAM chips at low cost. And the fundamental idea is what I described. You use analog computation capability, and you usually activate multiple rows to perform computation. I'm going to give you some examples of this. And you get significant energy and performance improvements. OK, so let's start simple. Not even talk about computation. Let's talk about data copy and initialization. So there are a lot of applications that require data copy and initialization. For example, imagine starting up a 10 terabyte database. You need to initialize the entire database at some point. And that takes a long time. And for security purposes, when you actually release a page, the operating system initialize pages, right? And there are many, many applications of data copy and initialization. And Google, in that paper that I mentioned earlier, showed that two system calls, memset and memcopy, occupy 5% of the execution cycles in all of their data center workloads. This is fascinating. Only two system calls, memset and memcopy. And these are essentially data copy initialization. And they basically, in the same paper, say that approaches like what I'm going to describe, which came before their paper, are very interesting to eliminate that overhead. OK, so what's the approach? Essentially, if you want to copy a source page, the white page over here, to this gray page over here, today you have to go through the processor, right? But there's really no reason to go through the processor. If you ask this question to, again, a 10-year-old, let's say, and say, how should I move? How should I copy the data from the white page to the gray page? Probably they will say, just move it inside the memory, right? They won't go through the processor. It's really actually, it's good to think about a child, think as a child probably today. So we don't want that because it has a lot of cost. We're just going to do copying inside memory. And we're going to exploit the existing structure of memory to do this copy. So this is going to be low latency. This is going to be low bandwidth utilization on memory bus, which is actually the bottleneck today. This is going to cause no cache pollution and no unwanted data movement. I'm going to show you a mechanism that takes, without optimizations, a 4 kilobyte page copy from 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. These are large improvements, clearly. So the idea is very simple. Remember that picture that I showed you of rows of DRAM cells? Each row, assume that it's 4 kilobytes. This is a DRAM subarray. And there's a row buffer, which is essentially an array of sense amplifiers to amplify the data, because the data charge that's stored in each cell is very small. You have to amplify it. So we're going to first activate the source row. When you activate a source row in DRAM, it brings the data into the row buffer, sense amplifiers. And then we're going to activate the destination row while deactivating the source row. Now, if you do this, the data that was captured from the source row into the row buffer gets driven into the destination row, because sense amplifiers are strong structures that will drive the data into the cells. That's the idea, basically. The idea is very simple, and all of the circuit principles support it. And we've shown that you just need 2 consecutive activates, negligible hardware cost to make it reliable. And this reduces your latency significantly and reduces your energy even more significantly to do this operation. OK. So this is nice, I think. And I believe this is just a step. Later work used some of the FPGA-based infrastructures that we developed to show that you could actually do this in a lot of real DRAM chips by violating the timing parameters. So normally in DRAM chips, you have a timing parameter between 2 consecutive activates. If you violate that such that it's almost 0, you get what I just described earlier. And this is real DRAM chips that are not designed to do this. But you can do it mostly reliably, very reliably. So this shows the capability of DRAM to actually do data copy. And initialization is a special case of data copy. OK, so we've actually built our infrastructure to do this on FPGA-based systems. And we have an FPGA-based infrastructure, if people are interested in exploring this, where you can write a program, and the data copy operations in the program get translated into the memory controller. And the memory controller does the data copy operation. And you can see the end-to-end result going through the data copy being done in DRAM. OK, we can see a picture of it also. And we see significant performance improvements. I'm not going to bother you with these numbers, but you can ask me questions if you want. OK, so that's interesting, but that was data copy. You can say data copy is interesting, initialization is interesting, but it's not computation, and I agree. So we can also do computation. So how do we do it? I'm going to show you in DRAM, but these ideas are also applicable to new memory technologies. In fact, new memory technologies, of which there are many, are very interesting because they can operate with minimal data moment, because fundamentally, when you access a cell in an emerging memory technology that's non-volatile, you don't destroy the data. In DRAM, you do destroy the data, so you have to move it a little bit to do computation. So let me introduce this idea. We basically introduced triple row activation. You have 3 rows in DRAM, A, B, C. I'm showing you only one cell in each row, but imagine that it's a 4 kilobyte row or 8 kilobyte row. And this is a bit line over here. This is the capacitor, and this is the access transistor. If you activate all 3 rows concurrently, the access transistors will connect the capacitors to the bit line, and the bit line gets perturbed, essentially. Now, if at least 2 of these cells are charged, you get the charge state at the end. If at least 2 of these cells are discharged, you get the discharge state at the end from circuit theory. And we know what that is, right, as a Boolean function. It's a bitwise majority function. So if you actually activate 3 rows, you get a bitwise majority function in DRAM, large scale, all 4 kilobytes. And if you actually are doing it in thousands of subarrays in DRAM, you can do this operation, bitwise majority, on 4 million bits in DRAM. So it's very large scale because there's a lot of parallelism in memory. OK, this is nice. Now, if you actually take C out, if C is set to 1, you get the OR of A and B. If you get C is 0, you get the AND of A and B. So you can do AND and OR. We're still not functionally complete. We need a NOT or just an AND. But we actually introduced some modifications to the DRAM circuitry to take. So if that actually exists already. So if you want to activate one row, the other side of the sense amplifier, the other end of the sense amplifier, has the inverse of the cell that you're activating. Right? You can actually feed this information back into the array or somewhere else. So DRAM chips are actually already capable of NOT operation because of this cross-coupled inverter that is acting as a sense amplifier. So it requires modifications to DRAM chips, though, to actually supply it. So we can actually have functionally complete operations. I'm going to update this later on in a slide. So if you're functionally complete, if you can do bitwise AND, bitwise OR, bitwise NOT, bitwise majority, now you can rethink your applications to actually and rewrite them in this manner, such that you can exploit the large bit-level parallelism in DRAM. Some applications are already exploiting this. People are building databases that use large bitmap indices that use these bulk bitwise operations. In fact, some databases are designed specifically for that because they wanted to accelerate those databases on GPUs and to exploit GPU parallelism. In general, a lot of the parallelism that you can exploit in GPUs, you can port it to this sort of parallel memory structures also. And then people are also writing web search engines in a similar way. OK, so we've done a lot of experiments, a lot of simulations on real workloads, and we see significant performance improvements and energy improvements that I don't show over here on databases, for example, in simulation. And this is the paper that introduced the idea. So how do you take advantage of it in a better way? I think in order to be able to take advantage of it in a more programmable way, one way is actually telling the application programmer, figure out how to exploit this. Another way is actually integrating this sort of acceleration capability in the programming language and the tool chain itself. And that's what we did with this work. Basically, if the user wants to, for example, accelerate some particular application, they built logic gates for it. So user input can be AND or NOT logic. This could be matrix multiplication, for example. This could be convolution. You could express anything essentially using logic gates and some interconnect between them. And then we use some CAD tools that were developed for quantum computing, actually, to generate majority inverter graphs. And then we translate those majority inverter graphs. This is essentially a simplified version of this logic that uses majority and NOT operations. And then we turn them into commands like triple row activation, row clone, etc., that correspond to the operation. Now you can actually have instructions that are encoded using the sequence of DRAM commands, which we call microprograms in this case. And when the application calls, for example, a convolution operation, this instruction gets shipped to the memory controller, and memory controller goes to the microprogram and executes it based on the principles that I just told you, executing bitwise OR, bitwise NOT, bitwise majority, etc. So this is a full tool chain, and we've shown that you can actually port many applications relatively easily to this in-DRAM substrate. It's all in simulation, of course, because we don't have real DRAM chips capable of this yet. And we see significant performance and energy improvements compared to both CPUs and GPUs. Okay, there's more over here. I'd be happy to talk more. I know I'm going relatively fast, but there's a lot of interesting things. Okay, so we need more flexible processing. Again, I'm going to leave it for potentially Yale's lecture. There's more going on here. That's very interesting, I think. Okay, I will not talk a lot about this, but essentially, if you want to do complex computation, so bitwise computation is relatively simple, right? If you want to do like multiplication of two 16-bit integers, this is not relatively easy in bitwise computation. You need to do bit serially, and bit serial execution takes some time, and then there are data mapping issues, et cetera, that you need to handle. But if you have actually use memory as a lookup table, such that you query memory with the inputs, and the memory gives you the output of the multiplication operation, for example, you can actually get significant benefits, as we show in this work. I'm not going into detail again. You can feel free to ask me in Yale's class. So what else can you do? Now, if your mindset is free like this, I think you can imagine a lot of things. And that's what I would encourage people to think about. You have a memory structure. What can I do with it? Not as memory, but computation. And we've done some of this. I'll skip this one. I'll talk about this one. These are two sides of the same coin. Basically, if this is done with real DRAM chips. If you have a real DRAM chip, normally you need to, when you activate a row, essentially you need to wait for some time for the circuits to settle so that you can read the correct data. What if you violate that timing? If you violate that timing, what happens is circuits settle in such a way that is dependent on the noise in the sense amplifiers and the bit line. So this is a very random, true random process. It's a physical process. So if you actually violate the timing in real DRAM chips, you can get true random numbers in some cells. And that's what this work is all about. Essentially, you can generate true random numbers in DRAM. Why is it interesting? Well, if you want to push computation into memory, if you want to push computation into memory, you need some, if you want to push security functions into memory, you need some random number generation. For example, if you want to do encryption in memory, you need random number generation, right? So I think this is actually fascinating. And then we've actually looked at other ways of doing this, which I'm not going to tell you more about, but there are better ways of doing this also. And we found even better ways that we haven't written up yet. Okay. So actually, DRAM chips today are quite capable. Whatever I told you earlier, like bulk bitwise operation, we showed that in simulation. But by violating the timing parameters, you can, in this upcoming paper, we showed that you can actually activate, let's say, 48 rows in DRAM. And you can actually build any operation that we know of, including NOT, inverse operation. Again, I'll leave the suspense over here. These are real DRAM chips. These are not supposed to do computation. We are able to do this because we have an FPGA-based infrastructure where we have an FPGA-based memory controller. We can program that memory controller, and we can violate the timing parameters, and we can see what's going on to the data that's in DRAM. I believe there's more to do. So if real DRAM chips, even though they're not designed for it, are able to do this, imagine what else we can do if we actually design memory chips for computation. Okay, there's more here, but I'm going to stop. How much time do we have? Oh, there's a question in the back. Yes. Two slides. This one. What? Forward one. This one. Yeah. Yeah. So we have a metric, essentially a reliability metric. You don't get all of the bits correct because the chip is not designed for it, right? So there's a success rate. We can actually improve that reliability. But again, the chip is not even supposed to do any of this, right? COTS is a commercial off the shelf, which was defined in the previous paragraph, which I cut. So there needs to be clearly more work done to make this a viable execution model. I'm not suggesting this is a viable execution model. Maybe it could be if you really know your application and the error behavior of your chip. Who knows? There are people who may be interested in trying it, assuming they actually know how to do the entire stack. But if this is supposed to be viable, I think the DRAM chips need to be changed to perform these operations reliably. Did I keep going or? 10 more minutes, okay. Any other questions? Yes?
Do you think you can get 100%
Yeah, that's an outstanding question. I don't know. I mean, clearly we have not gotten it. We tried. What you can do is add redundancy, which is not good. Basically, you don't perform this operation on one copy of data, but many copies of data. And if you can actually activate 48 rows, actually we've seen in some cases many, many rows, like thousands of rows can be activated concurrently due to the operation of internal logic in DRAM. You can add a lot of redundancy to get higher reliability, but 100% is very tough, I think.
Yeah. Are there like use cases when you don't have 100% reliability?
I believe so. I mean, we have not examined that, but a lot of machine learning, a lot of statistical applications are error tolerant. In fact, we've exploited that in related work, and also many people have exploited that in previous work. Some graphics applications may be tolerant also if they interact with the user and the user doesn't recognize the problems. So I believe so. But it has to be done very carefully.
How many products actually do this?
How many products are capable of doing this? How many products are capable of doing this?
How many products are doing it? Not capable of doing it, but are doing it.
No. What is it, I think? What is it? It is what we've demonstrated, or?
Using this kind of knowledge.
Oh, this is not appeared yet. This paper has not appeared yet.
So you're going to tell me that this is the first paper that dealt with any of this using memory?
Oh, yeah. So okay. Yeah, sure. I see. Yeah.
We come up with these ideas,
Mm.
and we think it's brilliant. And industry knows about all these years.
They don't know about it.
They don't know.
I will argue that, yes.
So you take exception to that comment?
Yeah, I take exception to that comment. They claim they know everything, but that's not clear to me.
Only to Onur Mutlu.
I'm not suggesting that. No. I'm not suggesting that. But okay, let me take a step back to answer.
So it turns out that in my dissertation, which I
Sure.
did write,
Yes.
but almost 60 years ago, I came up with a module which allowed you to design circuits
Mhm.
and use half the number of packages,
Mhm.
which meant even better reliability with respect to the pins, which is where the reliability problem is most prevalent. And I went, wow, we just adopted
Sure.
this. And,
Yeah. Okay. I mean, you want me to go to the adoption slide? I will.
Gave talks. How many companies do you think adopted?
Zero.
Exactly.
Yeah.
Like a lot of things going on here that I
Yeah.
don't think you can.
Yeah. I agree. Yeah. I absolutely agree with you. I mean, we're on the same page. Basically, how many people do it right now? I believe it's zero. But does that mean that it should stay zero? I don't believe so. That's why I think we need to work on it. So both using and near memory, actually, using is actually much worse. Near is better. Both of them have adoption challenges, but maybe you have a comment. Yes. Mhm. That's correct. Mhm. So in this case, basically, we're activating multiple rows. It does increase the latency a little bit, but we're violating the timing parameters also. So we're actually reducing the latency as well at the same time. So in DRAM, we don't have the endurance problem. Now, there's an asterisk over here. We don't fully know, but it's not as bad as any other memory technology. That's the beauty of DRAM technology, in my opinion. The effect of all of these on cell reliability, that's something we're studying right now, but I don't think we'll have the endurance problem. We may have other issues, like RowHammer being exacerbated by this sort of activations. Yeah. So basically, you can operate at the same level DRAM operates today, which is slow, of course, compared to transistors, but you exploit the large parallelism that exists in DRAM. So the benefit comes from huge parallelism and no data movement. Well, at least no data movement from the DRAM chip to the outside, right? Yes. Mm. Yeah, maybe there are some applications. Yes, we can talk about it. Okay, to address Yale's issue and also my issue, basically you can design. So I think Yale's getting at you can design anything, and you can be very happy with it. How do you get it adopted? I don't claim that I know the answer to this, but I believe we can work on it. As researchers, we can only work on it and figure out the ways of adoption. So there are many, many potential barriers here. And I think things are happening in the right direction today. Industry is actually looking at applications and software for processing near memory. I showed you pictures. Those are really important. What applications benefit? Are they really important applications? So with large language models, for example, there are multiple works from major companies as well as universities that are showing that large language models are so bottlenecked by data access that near memory processing can help. Ease of programming, of course, is really important for any hardware adoption. GPUs actually enable this. Let's say one company enabled this nicely, and they're taking advantage of it. So having programming models that take advantage of what's going on underneath helps. We need to think about system and security support. How do you do coherence if you actually partition computation between near memory or processing in memory and processors? Synchronization, virtual memory. Virtual memory is a huge mess, I think, in general, but I'm not going to talk about that. Again, you can ask these questions later on in Yale's class. Runtime and compilation systems and infrastructures to assess benefits. I think, but most important, in my opinion, mindset is the problem. Essentially, all of these we can work on, but we're swimming across a huge current. And the current is basically, there has been huge investment into the processor-centric system for over the course of 70, 80 years in all aspects of the stack, in ways that actually make people almost not even consider alternative solutions, right? This is business as usual. This is how you make money. And I understand that. That's how you make money today, right? At what cost? I think we should really understand the cost. And as researchers, we can do that. So how do you enable this adoption? I think it's happening slowly. It's probably going to be a slow adoption, evolution, as opposed to a revolution. But I believe it's happening. And again, this is not going to be the only execution model. CPUs are also very good at things that memory is not good at. And we need to actually invest in ways of partitioning computation in these heterogeneous type of systems. But I think in the end, it's all about the mindset. We need to change our mindset. Whenever you have a new type of approach like this, for example, data mapping, you need to map data differently so that you can actually execute on the data in a single DRAM bank if you're doing near memory or processing using memory. Today, that's not done. Today, data mapping is done such that small pieces of data are interleaved across different memory channels. Basically, consecutive data elements are in different memory channels, different memory modules. And you may not be able to do nice near memory processing if you want to aggregate between those different elements, right? So why are they, so the question, of course, you should ask is, why are they interleaved across different memory channels? To serve the CPU. This is a processor-centric mindset. How does the CPU get the maximum amount of data rate from memory? Interleave data across memory channels. But the mindset, if the mindset is data-centric or memory-centric, how does memory access the data it needs to do computation? You would have a completely different data mapping. So I think these are things that we need to question. But mindset is in the end the king. Okay, and also we need to revisit the entire stack. Are we done? Okay, I can go to the last slide if we're strict. No, it's not the last slide, clearly. But so there are many, many adoption issues, and these slides cover that. Yeah, I'm only at 200. I'm not going to go over that. Yeah, I have. But basically, just to give you an idea, I think programmability is a big issue, and people are working on it. We're working on it. There are actually papers written on this topic. I'd be happy to talk about it. There are other issues that people are working on also. The rest of the slides are about real PIM systems that you did not want to talk about. I'm going to skip them. But if you come to the Yale's lecture, maybe you learn about them. Okay, let me conclude. So I think we want to build fundamentally efficient systems and fundamentally high-performance systems. I think those are all data-centric. Those need to be data-centric. And we need to minimize the data moment in our systems. So I believe we must design our systems to be balanced, high-performance, energy efficient. That will lead us to intelligent systems. I'll pick the word balanced over here because one of the things that I learned from Yale very well is the importance of balanced design. If you take the microarchitecture course, there are 3 key elements of a microarchitecture, right? It has to be balanced. I'll leave you to figure out the other 2. When I teach a similar course at ETH, and I also tell the students that immediately we violate this balanced design principle from a system perspective by having processor-centric designs. So I think mindset can be changed through education, perhaps. So basically, we have a huge imbalance in our systems today. Processor is very capable, but it's being starved because nothing else is capable in the system. Okay, so I think we need to fix this. We need to enable computation capability inside and close to memory. This can lead to, I've demonstrated that orders of magnitude improvements, even with chips that are not designed for that purpose. This can enable new applications and computing platforms, I believe actually in this significantly, in genomics, in my opinion, and in some other in-sensor processing domains. This also can enable a better understanding of nature. If you have time, I'll quickly mention something. So I was fascinated by computing as well as psychology when I attended the University of Michigan. That's where I took Yale's course, freshman course at that time. I also took a psychology course. So when I took the psychology course, which was also taught by an amazing teacher, these psychologists were fascinated by computers. They actually literally introduced computers as a paradigm for understanding the human brain. That paradigm is gone. Basically, psychologists don't introduce things that way anymore because they quickly figured out that computing is very different from how human brain works. Yeah, they have to be congratulated. Okay.
Long time they accept that.
Yeah, yeah. So I think the future of truly memory-centric computing is bright, but we need to do a lot of hard work and work against a huge current. And that current is real. It's not just, I mean, I said mindset, but mindset incorporates thinking. It also incorporates business. So there's a huge investment in terms of business. So if you think about it, doing computation in storage, for example, there's a huge stack that you need to overcome. Okay, so maybe I'll leave you with this picture. So if I look at this thing that I believe is a device, it's doing some computing, clearly. Is it doing the computing that we're doing in our machines? I don't believe so. I don't believe imitating this device may not be the best approach. But if you want to understand this device and do energy efficient computation like this device, perhaps we should really look at the principles it uses also. And I don't believe those principles are processor centric. There's some, again, I don't claim that I know this thing, but there's a lot of integration of computation, communication, and storage going on in this device in a heterogeneous and distributed manner. Okay, maybe that was not my last slide. My last slide should be thanking my students because I presented their work and they've done a lot of interesting work over time. And if you're interested in finding the papers, they're online. And we actually put a lot of open source things online. So if people are interested in developing, working in this area, you actually have a lot of resources today, in my opinion. And that's where I'll conclude. I'd be happy to take more questions.
Yeah, so I wonder if you indulge me to point to one of your slides. We don't have time to deal with it, but I just want to make people aware of it.
Sure.
I think it's the first slide that you showed.
First slide. Okay, computing is bottlenecked by data. This one.
It wasn't the first, close to the first. And I think you made the comment that if we can only remember one slide.
Oh, okay, sure, sure. Yes, okay. Yeah, it's. Yeah, I went through it so fast that you think it's the first slide.
So, quarrel, what you want to talk, given what you're talking about, I'll quarrel with one term on that slide.
Okay.
General purpose.
Yes.
So you're familiar with systolic arrays?
Mm-hmm.
Systolic arrays today might be considered the FPGA if the data that is being generated is going to have to go through the same processing.
Mm-hmm.
And so you can start that processing in the FPGA as it's coming out of the data and just step it along and get a lot of the benefit that we're talking about. It's not general purpose anymore. It's an FPGA that can actually do parallelism at a much greater extent. Sure. And we can pick it up at 5 o'clock.
Yes. Any other questions?
Okay, for those of you that haven't had enough, Onur will continue at 5 o'clock. Maybe we'll get him to talk a little faster so let's get more in. Thank you very much.
Thank you.